I've decided to give this to my grandson, and I'm making this video for him, but I might as well make it public. So if everything's working correctly and the mail works and you're watching this video, you should have this device in front of you. It has a bail on the bottom that you can pull down in order to tilt it up. And as you can see, it's a Tenma Model 72320 oscilloscope. An oscilloscope is essentially a graphing device. In the horizontal mode, we have a line, and we have divisions. We have scales in both directions, and they're divided into fifths on this line and this line. The speed at which this line is drawn, and it's repetitive drawing, is determined by this knob. The time intervals on this knob are the time it takes to traverse one of these spaces. You can see what I mean if I slow it down. So I can increase the speed of the sweep by increasing this knob. Now it looks like a bunch of dashes, but that's really a continuous line. This is an artifact of the camera. So we have a line we can sweep back and forth. And that line is time. We can apply voltages to this line, and they will make it go up and down. And that is volts. So we're getting a graph of time versus volts. This oscilloscope has two inputs, so it could have two horizontal lines. Like that. Speed changes speed a little bit. See, there's two of the lines now. Of course, there's no voltage applied, so there's no vertical deviation. And we can display, although it's called input Y and input X, it's the same as channel A and channel B. We can display only channel A. We can position it up and down. We can display only channel B and position it up and down. Or we can show both inputs on the screen. Provided you with two probes. Let's take a look at the probes once. The probes fit on here, and they lock. You can turn them to lock them. So this turns. We have a little screw here, I'll get to that. We have the probe itself. In this configuration, pulling back on this exposes a hook. See that hook? Pulling the end off exposes a probe that we can touch to things. There's a switch here that's marked X1 and X10. In the X1 position, whatever voltage is applied here, comes out the connector. In the times 10 position, 1/10 of the voltage applied here comes out here. Now, the nice thing about an oscilloscope is that has its built-in signal generator. So I'm going to put the probe in channel A, lock it, with the probe hooked to channel A, the switch in channel A position. I'll put the hook on this calibration signal. Now, according to this calibration signal, it says it's a half a volt peak to peak. Well, that's peak to peak. I've turned the switch to 10 millivolts per vertical division. 10 millivolts. But the probe is in the times 10. So instead of a half a volt coming out, I have 0.05 volts coming out. We'll adjust this to get this lined up with the graduation and this lined up with the graduation. 1, 2, 3, 4, 5. That would be 50 millivolts. But because of the 10 times dividing probe, that actually is a half a volt, which is what it's supposed to be. So we can measure voltage now. This is only accurate if this knob, the red knob, is in the calibrate position. Okay? This is supposed to be a square wave. That doesn't look very square. The little adjusting screw I talked about in here, let me adjust that screw a little bit. See what's happening? I'm bending the top and the bottom. What I'm trying to do is get this perfectly flat on top. That matches the probe to the oscilloscope. So if you are reading voltage and you are off by a factor of 10, check this switch. I put it in the times 1 position. And you see what happened? It got very big. Let's pull it back down. Adjust it again a little bit. We are at, that's a half a volt per division. I'll hook the other probe up. So now I have 2 probes hooked up. We'll look at display B. Crank it up till we get it somewhere. And once again, I'll have to tune the probe to match the oscilloscope. There we go. So that's B. There's A. And I can display both of them simultaneously. Move B up a little bit. There we go. These are not moving left to right. They're stationary. They're being painted. We can measure the time by looking at this, time per division, but we have to get it synced. See how that's all messed up? And I'm rotating this slowly. All messed up. Now, if this knob is pulled out, that way, pulled out, it will continue to sweep across the screen, but not necessarily stationary. If I push it in, didn't do anything, but watch what happens when I turn it now. We don't see anything. So when you put this thing in action, at least initially, pull this out. That means even if you don't have a signal displayed, you'll get a line. This box up here, this and this and this, allow for synchronization. This is the level, that's the voltage at which it syncs. Right now it's somewhere between here and here. I'll show you with the sine wave in a little bit. This decides whether we're triggering on rising or falling voltages. This is normally left in the AC position. There are situations where you want to synchronize off something else. So, and this decides if we're syncing off of channel A or channel B, or the 60 hertz line frequency, which you probably won't use, or some external sync, which is entered here. So, leave these three switches up, leave this out, and at least it may not be synced, but there'll be green lines. Now, we have the ability to magnify by a factor of 5. It magnifies around this axis. So we're looking down here at this little flat area. We'll magnify it by 5. Now we're looking at the little flat area, except it's bigger. This is just an on and off switch. This is intensity, how bright the trace is. And this is focus, whether the trace is sharp or not. You should need to adjust it, but this will rotate the trace. Channel B can be inverted. Let me hook a sine wave into channel A. Looking at the little line here in the sine wave, that's where we grab the signal and then paint it. But I'm only syncing on channel A. And so channel B is slightly different in frequency from channel A. I can't synchronize both of them at the same time. I can choose to synchronize off channel B. So I'm synchronizing off channel B. Channel A is free running. Synchronizing internally, which is off A automatically. If I want to synchronize off B, I throw this switch down. I can vary the frequency of the sine wave, and you see I can compare frequencies. When it's not moving, they are almost identical. Well, when it's not moving, they're identical. So we'll go back to just channel A, move it down, give it some gain. So if you just look at channel A with this switch out, these switches all up, this switch up. It should display whatever you feed into it. Now, the inputs each have a switch, and that determines what information passes through here. In AC mode, only the wave itself passes through. In ground, nothing passes through. In DC mode, if there is any DC, it will be offset vertically by the amount of the DC. Let me add some DC. Introducing DC into the waveform. I got to be careful. If I introduce enough DC, I'll take it out of the synchronizing range. I have to resync it. You can tell where 0 volts are by putting a ground into it. You can adjust the position vertically so that the 0 DC falls on the reticle. Now we'll look at AC. AC will be centered around 0, assuming it's a symmetrical signal. DC may not be centered, depending on whether there's any DC coming in as well as AC. I always, unless I'm doing something special, leave these on AC coupling, unless you really want to measure the DC component. I'm inputting the square wave here. I can adjust the horizontal position as left and right here. So let's line one of these up. I'm going to line this one up with this line. So each division, according to the switch setting, is 0.5 microseconds. So two of them, this one and this one, would be 1 microsecond. All right, a microsecond is 1,000th of a second. A complete signal is from here to here. That is this line and this line, back up to here. Okay? So if each little division takes a half a microsecond, from here to here takes a microsecond, or 1,000th of a second. And in fact, that's what this output is. A 1,000 hertz signal. Remember, a signal is the complete positive and negative swing. So in addition to measuring voltage using this, I'm running the channel B, using this scale, I can measure time, repetition, using this scale. Again, it's only calibrated when the red knob is in this clockwise position. And you'll notice there's an arrow that says calibrate. So we don't know what the repetition rate is now, but there are times when we want to adjust the repetition rate to provide the signal somewhere in this viewing area. If these red knobs are all completely clockwise, these dials are accurate, or as accurate as the scope is. Now I'm on channel B because you can see I put the switch in the channel B position. Channel A is on the sine wave, which is coming from my signal generator. Move the signal generator to 1000 Hertz. And I'll display both of them, which is in the dual mode. My signal generator is not too accurate. That's pretty close though. I'll try to find a manual for this. If it's not in the box already, I'll try to find it. But keep these switches up, this switch out, and just hunt around with frequency and voltage until we get on scale. You can position it up, down, left, right. It does have a feature where you can add these two signals together. Sort of weird. Now this does have a component tester. You can turn it on and off here. You'll probably not use that. It has an earth ground connection here. And these probes are provided with a grounding connector. So in theory, when you are probing using the hook or the needle, you want to connect this to the chassis of whatever you're looking at. Now, be aware that this connector here is connected to earth ground. So don't try hooking this to a line side of the power line. You'll blow a fuse or you'll burn up the oscilloscope. This whole thing here and here is connected to the grounding pin on the power connector. So be very careful. Think about what you're doing.